All right. Okay, so this video, or probably going to be sets of videos, uh, in this in these videos, I'm going to discuss the graphing of motion, and there's going to be some uh, relationships that I'm going to show you that between the graphing and the deriving the kinematics. In particular, I want to show you how with a graph you can get the second kinematics equation, x minus x naught equals v naught t plus 1/2 at squared. And I think it's verging on beautiful how graphically you can derive the same equation. And so look out for that in this video or maybe the next video. All right, let me just keep some room here. Get rid of that real quick. Okay, so I had a little hard time figuring out how to organize this video. And I think I decided I just want to draw graphs and explain the graphs as I draw them. I'm going to start out just drawing position versus time and velocity versus time graphs. Velocity, that's a V, versus time graphs, leaving space over here to come back later to talk about acceleration versus time graphs, but we'll do that later. And so whatever I draw on the position graph here, I'm going to draw the equivalent velocity graph. So if I start a new set down here, which I will eventually, that's going to be different. So let's disregard that for now. All right. Let's try this one to start with. All right, let's say we have a graph that looks like this. Let's see, let's try it again. So basically what this means is someone is standing at a position of 5 meters and not moving. How do you tell? Well, the y-axis is your position, and so you're at 5 meters during the whole time. That means you're not moving. All right? What would that look like for velocity? Well, if you're not moving, your velocity is 0, so for the whole time, your velocity is going to look like that. Not too bad. I always like to start off a little easy. And what's another good color that I think this might work on this? What happens if you're standing over, oh gosh, over here at -5? Does that change your velocity graph? Well, you're still not moving, right? It actually doesn't matter where you are, you're still not moving. So your velocity graph is going to be the same. And you're going to find that's the same for any type of graph. If your graph on the position graph has the same, it looks the same, even though you start at a different spot. So what do I mean by that? Well, you could have a graph that looks like this. Whoa! Of course, you're going backwards in time here. That's not legitimate. But just for illustration purposes, if you also start up here and go, whoa, so that's supposed to be the same graph as the blue one, then your velocity graph is going to look identical. Doesn't matter where you started, your velocity is still doing the same thing. Let's quickly get rid of those ugly graphs. All right, makes sense. So that's not too bad. All right, let's try a different set of position graphs. Let's see, position 0 time, velocity, velocity graph. This is 0 axis. Let's say now our position is changing. So we start up here. Let me try to make neater lines using this tool. So, and using this color. So now let's say we start at 5, but let's not do that. Start at 5, but now we walk in this direction. What do I mean by this direction? Well, it looks like if we start at 5 meters, pen, and we're heading back to 0 meters, looks like we're walking backwards towards the beginning, towards like the starting line. But then we keep going past that and keep going even farther backwards into the negative area. What does the velocity of this look like? Well, remember, velocity shows how fast you're going and direction. So the direction is important here. We just determined that we're going backwards towards the negative area. This is like negative land, and this is positive land, right? Think of a track. Let me draw a track quickly. All right. You don't use all the track. If you're doing the 400 meter or the mile, I guess you use the entire track. But if you're doing the 100 meter, you don't use the entire track, right? So the starting line for the 100 meter might be here. Start at 0 meters. And over here is finish at 100 meters. So you could go this way, and usually we call that the positive direction. So this is like positive area over here. But let's say you twist your ankle at the starting line. You're like, I can't race, so I'm going to just walk back this way towards my coach and cry. Then you're going in the opposite direction, kind of towards negative space. Or you could have started the race and broken your femur about here, and then walk back. Well, you wouldn't really be walking back. You crawl back to your coach. Be like, Coach, I busted my femur. Ow. So you start off going in positive land, and you turn around and go backwards towards negative land. That's kind of what's going on here, except the track is the y-axis and time is the x-axis, so time kind of spreads out your motion. Right? Anyway, let me erase this because acceleration graph is going to go there someday. So what does the velocity graph for this look like? Let's keep using that nice modifier. So if we're going in the negative direction, we're going towards negative land, then our velocity, the direction of our velocity has to be negative. And so it's going to look like this. Now, why is it this and not this or that? Well, how fast you go is determined by how much distance you cover in a certain amount of time. And if you break this line up into different chunks of time, you're going to find that you cover the same distance in each chunk of time. So in 1 second, you've gone from maybe here down to here. In 2 seconds, you've gone from here. In the second, I should say, let's keep my language clear. In the second, you've gone from here down to here. You've gone down the same distance as the first second. In the third second of time, you've gone down the same. Anyway, what I'm trying to say is the slope is not changing. Therefore, your velocity is not changing. I brought in the word slope now. I went there, yes. So let's talk about slope. In short, the velocity graph, this might be worth writing. I don't know if you guys are taking notes while you watch these videos or how you are utilizing these videos. You could just watch them over and over again, I guess, if you needed to. But if you're taking notes, you might want to write down the stuff I write down or even just the stuff I say. But sometimes I feel like writing things down helps us remember things. So slope of position versus time graph equals, well, I'm just going to say equals your velocity versus time graph. That's not really worded very well, is it? The slope of your position time graph tells you the value of your velocity time graph. So if the slope is negative, say the slope of this line is negative 2, just for the heck of it, then your velocity is going to be at negative 2. And if your slope is not changing, if it's always negative 2, your velocity is always going to be negative 2. And to be consistent with the first graph, let's say we start. Now you go back, you're already back at where your coach, you're back with your coach, and your coach is like, suck it up, go race, I don't care if your femur's broken, it'll heal later. And you're like, I hate you, coach. But anyway, you go back because you have no alternative, and you start walking back to the starting line. Of course, everyone's done the race already, but you're a trooper, right? And you're going to keep going to the finish line. So that's your motion. What does your velocity graph look like? Well, slope of the position graph equals the velocity graph. So your slope now looks about the same, 2. Depending on what units this is, meters per second. If your femur is broken, this is probably inches per year, or maybe some crazy long time and short distance. But anyway, the slope is positive, and so your velocity is going to be positive. And if your slope is not changing over here, then your velocity is not going to be increasing or decreasing. Your velocity is going to be constant. Make sense? Cool. And let's see here, 12 minutes. And I wanted to talk about, all right, I'm going to cut this video off at this point, and the next video is going to be graphs, position graphs that look like, whoa, this, or whoa, something like that. Anyway, I'm having too much fun, so see you next time. Stop here, there we go.